In many processes, there exist some unmeasurable variables. For example, consider this chemical reactor. To control the process, we would like to know about the outlet properties. We can measure the reactor temperature online, but concentration measurement is always with some delays. Today I am going to talk about moving horizon estimation, which is a computational technique to observe the unmeasurable variables in a dynamic process. Kalman in 1960 presented Kalman filter design to estimate the state of an unconstrained linear system with additive white noise. Unfortunately, most systems in engineering are nonlinear, so Smith with his colleagues immediately extended this method to nonlinear systems. He used Taylor expansions to linearize the system about the working point. However, this method cannot handle the constraint on the system states and input. 30 years later, Michalska and Main proposed moving horizon estimation method for nonlinear and constrained systems. To show the efficiency of MHE in comparison with extended Kalman filter, I provided an example from Rowling's paper. Consider a gas reaction with this stoichiometric coefficient and this reaction. As a result, the states of the dynamic system are the partial pressures and the measured output is the total pressure. This is the dynamic system with an initial point. It's obvious the state should be positive. The results show in EKF the estimated states are negative, while MHE estimates them properly. You may ask how an MHE works. Imagine you are a detective and a robbery has been reported in your neighborhood. What's your guess about the sex and age of the thief? A young man? In the second day, you will find a lipstick in the crime scene. So this time you will guess the thief is a young woman. On the third day, you'll find reading glasses. So again you would update your guess. The thief is an old woman. This is exactly what an MHE does. It finds the most probable state based on the past and current measured output. If I want to talk more technical, MHE uses sliding window. At each sampling time, the window moves one step forward. It estimates the states in the window by analyzing the measured output sequence and uses the last estimated state out of the window as the prior knowledge. MHE to estimate the states uses a cost function to estimate the initial point and the disturbance or noise exposed on the system. The cost function must include two terms. The first, called the stage penalty, penalizes the estimated noise in the transition and on output. The second term, arrival cost, summarizes the information which is now out of the sliding window. A typical arrival cost penalizes the deviation of the estimated initial state from the prior knowledge which is obtained in the last estimation. In many processes, there exist some unmeasurable variables. For example, consider this chemical reactor. To